So yeah, I said my name is Morten. I am from the Danish Technological Institute. We are we are actually exactly the Danish equivalent of VTT. So we are similarly a self-owned company, and our primary goal is to sort of increase competitiveness of companies by implementing technology. And I should really emphasize that it's this implementation of technology that we work with. And what I'll be talking about today is a tool that sort of makes it easy to implement a given technology. In this specific context, the AI technology of Bayesian optimization. So, what has already been introduced, I will focus on a very simple problem to state, which is to find optimal settings for a process based on a set of predetermined quality requirements. So this optimization of something that Arthur already spoke about. There are many ways of solving that problem, but one effective way is, and what we're focusing on today, is Bayesian optimization. And Bayesian optimization is just a mathematical technology that lives inside this software tool I'll be talking about called Brownie B. I should stress that in most of industry, even though Arthur showed very well that design of experiments is basically 100 years old by now, most of industry across the world does not use it. What is the typical status at many companies, particularly small and medium-sized companies in our experience, is that they use one factor at a time optimization, which is an extremely ineffective way of solving this problem of finding optimal conditions. And it's probably because we're taught this already in basic school as part of sort of the science classes, and it's in many cases never really sort of walked back upon or challenged even through higher education. And in this approach, we might have a process that we think might depend on time and temperature. And a typical chemist, such as myself, I'm a chemist by training, would often go out into their lab in an R&D environment and select a fixed time and then run a temperature series and see the quality is best here. And then they would sit on that temperature, run a series of time points, gather data, and see that the optimal condition is here. And this is extremely ineffective for anything that is moderately complicated, simply because there's no guarantee that you will find an optimal solution, even when it exists within this playing field that your factors are sort of defining. And it becomes sort of very confusing and complicated to keep track of what you have tested if you just do this in an Excel sheet or on a piece of paper, which is, again, what most of industry does today. As Arthur also mentioned, classical DOE was sort of invented to try and take the approach that if you want to figure out how a process behaves, you should draw a map of that process and use it to find your way to the goal. So in classical DOE, you would typically choose a bunch of experiments up front in this way, designed to draw the map of the process or the product performance. So these 9 data points would be used to draw this landscape, so we can use the landscape to predict that this is where the solution is. And in principle, this approach is a much more sensible way of attacking this problem than the approach here on the left. But in very many practical realities in many companies, the amount of experiments it requires you to do in order to draw a realistic or useful map of a complicated problem becomes very large or practically intractable in many contexts. So this is where Bayesian optimization sort of comes into its own right and provides a much more, you could say, appetizing alternative to classical design of experiments. As Arthur showed, at its core, Bayesian optimization starts out collecting data at a few points in your sort of possible solution space, and then it draws a model or a landscape, as I like to call them, that we know is very wrong, but that landscape still contains some information that allows us to calculate where should we do the next experiment. In my animation here, I've sort of highlighted it as a yellow color. So you could think of it as, of all the possible settings I could choose here, the more yellow, the more productive it is to run an experiment in those conditions. And the Bayesian workflow is simply to then go to these conditions, gather data, redraw the map, ask for a new set of settings, and so on in an iterative fashion until your landscape stops changing or you find a solution that's good enough. And on the whole, you could say that the algorithm here in Bayesian optimization is really designed or appropriate for the case where it's the solution that is important. Basically, you need to find the right recipe as fast as possible, and you don't care about all the recipes that are bad. In the DOE, classical DOE framework, that is really appropriate when it is the map itself, so the model or the full description or the full understanding of how the factors interact with each other. When that is important, then DOE is still a really good method. But from the vast majority of companies, this is much more aligned with their project goals or their development goals in many cases. So let me just sort of try and qualify this further and show the strengths of Bayesian optimization with a concrete example of something that classical DOE is hopeless at solving. And that involves a complicated chemical reaction such as the PCR reaction. So this is the kind of stuff that happens inside COVID tests to sort of amplify the DNA of when you check for COVID. So something like a PCR reaction has a bunch of settings that we could change in order to optimize the quality of this chemical reaction. So in this case, quality is maybe the effective yield, so the yield times the purity, for instance. And if you were to attack this problem with classical DOE, it's really not very appealing, or it's very, it requires a lot of work to do. Because you would typically start out trying to eliminate some of the factors by what's called a screening experiment. And then you would try to draw the map in the using the factors that are active or that you see are relevant for quality, which in this particular example would require almost 100 experiments on its own. And for a problem of this complexity, you would therefore, in a very optimistic case where I am assuming very good data quality, need to run something like 120 to 160, maybe 200 experiments just to figure out whether there is a solution to be found anywhere. And to make matters worse, when we are working on a process where we don't have a lot of domain knowledge, classical DOE tends to favor looking in the corners at the extremes to sort of highlight the differences that different factors make. But when we don't know processes very well, the corners might not even work at all and give very uninformative data. And this is one of the sort of practical reasons why classical DOE is underutilized in many company contexts. That is sort of the mathematical argument. The other argument for why many data-driven techniques are not really used much in industry has to do with humans. So most scientists to this day in many companies still think that one factor at a time is the right strategy. And they're very confident in that belief. So when we, in my institution, go out into companies and try to teach them to do something different, we have to kick them off this mount one fact at a time and teach them something slightly more about designing experiments. But then if we try to teach them classical DOE, they get really scared by how many experiments you have to run. They might not really know how good their data is and how their measurement systems work. Or even worse, they might not have an objective measurement system. They might just gauge quality by looking at it. And in many cases, particularly if classical DOE is introduced to a company, they will say, I don't want a map of my process. I just want to find a good recipe. So I like to call this, this region, when you try to teach people to use something better than one factor at a time, the valley of despair. And it would be nice if something existed that was able to drag these people across the valley of despair in a simple way so they could at least get started doing something that is better than one factor at a time. And this is what Brownie B is designed to do. So let me again now apply sort of the same, or take the same problem and show you what Bayesian optimization would do here. So with Bayesian optimization, we still have this PCR reaction with lots of things we can control. And we would start out just like in classical DOE to define factors that we would change. And then we would go out and do a limited number of experiments to begin with. So in this case, we want to increase the yield of this reaction. So we pick 15 initial very different ways of running this experiment and gather data here. And these are then the results in this example. So the empty circles is where we got complete flatline response, no signal at all. And the blue circles is where the signal is in some cases very low but detectable, and something above 0. So basically all of these reactions worked really poorly, but they didn't work equally poorly, all of them. And since they were, created with different settings, there is some information here that could potentially allow us to choose a new set of experiments that might yield a better result. So this is what Bayesian optimization does, is it just incorporates each result as it comes in, chooses a new set of settings in an iterative fashion, constantly refining its guesses until we, in this case, we reach our result. Now, maybe this was good that this was what we had the budget for, but in some cases we might also wish to continue and with us, because now we found what we wanted to get to, 500, and maybe we're curious about whether we have plateaued. So I'm just going to sort of bump the goal up to 1,000 and continue for a number of iterations for this particular problem. And in this case, after 35 runs, we have far exceeded the initial goal on a system that is extremely complicated. And again, I showed you for comparison, DOE to even get started on this would require, on the order of 5 to 6 times more experiments to run to make any headway on this problem. Right. That's just to sort of show you the kind of complexity where Bayesian optimization really shines. But in order to make it easy, we have built a tool that sort of abstracts away the math that's happening and simply guides you towards how to pick your experiment. And we've built this in a browser in a collaboration together with Novo Nordisk, where that Søren is from, and he'll be talking about that in a second. So let me just change and show you live what this looks like. So Brownie B lives on the website brownieb.io, where I have the unfortunate fate of being the face of teaching people how to use it there as well. But you can try it out for free on this website and simply by registering. I have already registered, so I'm just going to log in. And just to show you how the process works, we're going to create a small experiment. So when I press this create button, it creates a new project for us, and we'll call it FCAI webinar. And we can add a couple of factors. So maybe we are interested in baking a cake or something like that. And we'll need to add some flour to our recipe that we might want to change between 200 and 500 grams. We might want to add some sugar between 50 and 150 grams. And we might want to use eggs in our recipe between 0 and 3 whole eggs. And since I don't want to break eggs apart, I want to only get suggestions with whole numbers. And then maybe we want to add some food color to our dough or something like that, because if it's for a birthday cake for a kid or something like that in this example. So I'm just going to go with red and blue. And you can see here that this is basically where I add our factors one at a time with the limits. And as I've done this, Brownie B has begun suggesting a set of these initial experiments that it would like us to go out and do in order to get started. And as we scale up the system, Brownie B will suggest more and more experiments to get started, because you need a certain minimum amount of information before the algorithm can really work. But once we're ready to start experimenting, we'll transfer them down here. And then it's off to the kitchen or to the lab to carry out your experiments. Now, Brownie B expects you to tell it about the system you're trying to optimize by telling it about the quality you observe. And in this system, quality is a fixed scale between 0 and 5, just to make it intuitive that obviously you want to reach 5 stars, if you will. So you have to use this tool. You have to be explicit about your goal and how you want to map it to this scale of between 0 and 5. And in this short webinar, I'm not going to there's a couple of videos on that on the Brownie Bee website that you can look into. But for now, let's just imagine that we are just talking about a cake quality that we are asking people to Now for this, it's just a bit quicker. So now once I've gathered results for these initial experiments where we use a low number of those, Brownie Bee will then actually begin, building a model for the system. I'm just going to ask it for one next experiment. And based on the results that we've seen so far, Brownie Bee is now using this Bayesian optimization algorithm to suggest a new experiment or a new recipe to go out and do in order to improve quality further towards a goal of 5 stars. And beneath our suggestion for the next experiment, it is also showing us its present best guess at the optimal recipe. So I've just made up this data, so this might not make sense at all. But basically, it's showing that it wants us to use about 410 grams of flour, no eggs, and the blue color. It knows the system. It thinks it has information close to this recipe, but where we don't have any data, the uncertainty is huge because this is already a moderately complicated problem, and we don't have a lot of data. Finally, here at the end, we have a histogram of what Brownie Bee expects the quality to look like if you keep producing at this recipe. So in this case, at this stage, it expects the quality to be between 4.2 and 4.7 if we just kept producing cake with the recipe that is shown in the predicted best solution. I just want to go out and show you just a bigger system. This is the PCR reaction example I showed you from before, just to show you what it looks like if you add a lot of factors with a moderate number of experiments here. And in this case, the process is a bit further along, and we can use these graphs to, for instance, see here that the denaturization temperature is best set to its maximum value, and if we reduce it, the quality is going to drop off. We don't know how bad it's going to be at the lowest temperature. We just have enough information to conclude that it will be bad. And on the other hand, the denaturation time, we're not very sensitive to because the dependency on quality compared to this factor is actually pretty flat, as an example. All right. Since this is a short webinar, I'm not going to dive into a lot more detail about this, but instead jump back into the PowerPoint and just continue with a few last points about this. So we have built Brownie Bee and designed the interface through implementation. So there's a bunch in Denmark that have been using Brownie Bee on problems that they were working on and provided feedback to make it more usable for people. That applying this in the real world is something we have extensive experience with, and in some cases, for instance, in the company Vestas Aircoil, who produce coolers for ship engines, it's significantly speeded up their sort of the pace with which they can develop a new solution when there's a customer request. Instead of, it's a process that normally takes 2 years for them, but using Bayesian optimization, they were able to produce a new product using complexity that they normally do in 3 months instead. You can read more about all these cases on the website too. So instead, I want to sort of highlight with 3 last points, just requirements and common pitfalls you should be aware of when you work with Bayesian optimization in the real world, and not just using Brownie Bee, but it applies to Brownie Bee as well. And I really want to state that Brownie B makes it easy to use a good method. And the inner side of Brownie B is really about the right side of this figure, which is about how you choose the next experiment. You obviously carry it out and rate your quality, and then update your model and use it to pick a next experiment. But very critical to this method is the first initial steps, which are not part of Brownie B as such. So I want to sort of highlight those, which you should be aware of there. So the first pitfall is about clearly defined goal. And many companies suffer from not having clearly defined goals, and therefore they commit errors of the third kind, which is the error you get when a specialist goes into the lab and produces a perfectly correct result to a different question than what their manager was asking them. And it is very important when using data-driven approaches that you are actually very clear about sort of the improvement that you're looking for, how many runs you can expect to get, and you have to consider these things and make them very explicit to make good use of data-driven tools. The second pitfall is this measurement of quality, so the response we get and the quality we tell a program like Brownie B, because it's still a data-driven technique which suffers from the CISO principle, which is shit in, shit out. So if you give it unreliable data, it's going to give you unreliable suggestions. And sort of being very explicit about how you measure quality is a very important part of using these tools. This is also why we force people to use a one number for quality in Brownie B, because it forces them to talk about how they want to translate their practical context to a number, which is often very valuable in and of itself. And the last point I want to make is about how we choose factors with domain knowledge. And I want to quote Douglas Montgomery, who's a very big figure within classical design of experiments. And one of his theorems is that you should never let one person design and conduct an experiment alone, particularly if that person is an expert in the field of study. And this sounds completely insane, but I want to sort of highlight a reason why this is particularly true in industry. And I really like, Mikko, that you asked the question about domain knowledge and making use of that. And it's actually, in my experience, very dangerous to do, or at least to over-rely on. Because in this example here, we have a process that's running at D setting. System, and we have tried temperature and time many times. So it's a stupid exercise to even try changing the system, according to our experienced colleague. Now, if we went out and repeated what this employee has done and changed the temperature, we actually see that changing temperature decreases quality. And if we change time in the way that our colleague has done so, quality also doesn't improve. So in principle, our colleague here is not wrong, or they have actually a good reason to say what they're saying. But as people who know classical design of experiments or are used to data-driven techniques will know, what they've missed by working with one factor at a time is that these things are synergistic. So you have to change both temperature and time to get a good result. And this is, in my world, one of the biggest dangers of relying on domain knowledge when trying to predict the outcome of experiments, is that quite often in environments where people have never used a data-driven technique for optimizing, they've actually learned the wrong lessons. So their domain knowledge is incorrect or incomplete as a result of that, because all they have is these straight lines through parameter space. All right, I won't harp on further about that. I just want to highlight that there's a bunch of companies already using Brownie B across the Danish industry, and maybe you want to give it a try too. It's designed to make it easy to get started with finding optimal settings for processes based on a set of predetermined quality requirements. And yeah, here's the website information. And I should say that the underlying math is open source and still being actively developed as a collaboration between ourselves and Søren from Novo Nordisk. And with that, I'll open up for questions and comments.